Hey guys, Mr. B here. Making you a video here for Math 2200 on section 6.1, Rational Expressions. So we're just starting the unit, and I thought I might give you guys a little video to help get this thing off to a smooth start. So all a rational expression is really similar to what a rational number is. Well, rational number is any number that can be written as a fraction, where a rational expression is just an algebraic fraction, where the numerator and denominator are both they're both polynomials. So an easy example of that would be something like this. So like x all over x plus 5. So that's just an example of a rational expression. Now, where this is going is eventually to solving rational equations and then looking at the graphs of rational functions later on. So what I'm going to give you guys is just an introduction to how we simplify these and looking at some restrictions and what we'll call non-permissible values of a rational expression. So we talked about restrictions when we talked about solving equations that involve square roots, radical equations. So we have that same idea here. There are some restrictions and some non-permissible values that exist with a rational expression. So here's an example of a rational expression. So try to think of some value that you'd put for x where this thing wouldn't exist. So you all probably guessed it, that if you had 0 in the denominator, of course we cannot divide by 0, and if you try it on your calculator to get 1 divided by 0, you'd get math error or whatever, you'd get something. Well, I have the graph of y is equal to x squared behind this question mark box here. And you can see what actually happens at this spot. This is what it really means to have a non-permissible value. So if you see right here where x is equal to 0 along this line here, it's actually the line of x equals 0, the graph is never actually going to touch it. It's going to come down and it's going to get really close, and it's just going to skim along by, but it's never actually going to get to x equals 0. So that's actually what it means to have a non-permissible value. It's a place where the graph or the function does not exist. Alright? So right now we don't have functions, we don't have graphs. We're just building up to that. So we're taking a rational expression and we're trying to determine where the non-permissible values actually exist. Alright, so here's a few different examples. So we have to look at where the non-permissible values. So the easiest way to find the non-permissible values for a rational expression is to take the denominator, this guy, so x minus 3, and that's a terrible x. I haven't made a video in a while, so my hand-eye coordination's off a little bit. So x minus 3 is equal to 0. So set the denominator equal to 0. You don't have to worry about the numerator, just set the denominator equal to 0. So we've done that. Now we have a little equation. Well, actually, x minus 3 cannot equal 0. So that's where the non-permissible value is going to come from. This thing cannot equal 0. So if we solve this guy, we have x cannot equal 3. So that's sort of the idea here, that we cannot have that value of x equals 3. So x equals 3 is a non-permissible value. So our non-permissible value is x equals 3. Well, same thing here. 4x minus 3 cannot equal 0. So we take that 3 across to the other side, divide by 4. So we're going to have a situation where x cannot equal 3 over 4. So that's our non-permissible value right there. So those cases here where you only have one non-permissible value are fairly straightforward. Well, there are cases where in this situation here, where if you notice we have basically a quadratic expression where this is factorable right here. Same with this one. These guys are factorable. So when we're looking for non-permissible values, we always have to make sure that we factor this situation. So we'd have this situation. X squared plus 4x plus 3 cannot equal 0. So this is a quadratic equation that you have to solve. These are most often than not, guys, when you're asked to find these, they're obviously going to be factorable. So you can use your rules that we learn. So AM method, I guess you could call it. What adds to get us 4 and multiplies to get us 3? Well, of course, that's going to be x plus 1 and x plus 3. I've gone back to the regular x, make my life a little bit easier. So we have that situation. So what that gives us is a couple little mini equations using basically the 0 property. So x plus 1 cannot equal 0. And then x plus 3 cannot equal 0. So you have those two situations that you have to solve. So this guy, x cannot equal -1, and this guy, x cannot equal -3. So those are our two non-permissible values. X can't be -1, x cannot be -3. If that happens, this thing will not exist. The reason I threw this one in there, D, is because this is a fact. We can factor this, but this is sort of a forgot about factoring technique. And when you have x squared minus 9 is equal to 0, of course you can solve this by just taking that across both sides. But this is also an example of difference of squares. And as we'll see later on when we're simplifying, that really important to be able to factor this type. So what this looks like factored is x minus 3 and x plus 3. And that should be cannot equal 0. So what I end up with is x cannot equal 3 or x cannot equol -3. So we have the situation where we have plus or minus 3. So if any one of these x values is that, then it doesn't exist. Now what you'll also notice, guys, you might take note of, you might be curious why, that I didn't touch the numerators of these things. So numerators do not affect the non-permissible values. You're only worried about when the denominator is 0. That's what we're interested, division by 0. Alright, so I hope that answers questions about non-permissible values. So, next topic we're going to talk about equivalent rational expressions, and where this leads to is simplifying rational expressions. Math teacher once said to me that there's only 2 operations in math, multiplying by 1 or adding or subtracting by 0. And this is sort of the same thing with equivalent rational expressions. We can do some stuff to this guy, and it's still going to be essentially the same thing. It's sort of like when we rationalize the denominator, or we take the conjugate and multiply by the conjugate. All we're doing is multiplying by 1. So if I multiply this guy by, say, 3, multiply the bottom by 3, so I'm multiplying by 3 over 3, essentially, I'm multiplying by 1. So I end up with 3x over 3x plus 3. That's still the same guy. It's still the same. And the same exists if same is true if I multiplied it by, something a little more complicated, like x. If I multiplied by x over x, so just 1, I don't need the 2 multiplication signs, it looks silly. So if I multiplied by 1, I end up with, x squared over x squared plus x. This is the same as that. This is just an equivalent rational expression. They look different, but they are much the same. Alright, so let's see what that actually means. So what that means is we can simplify rational expressions, and we still have the same rational expression, it's just in simplified form. So I'll take you through a couple of examples here. And one thing we must remember when we're doing this stuff, and I know I'm going through this kind of quick, guys, but one thing we must remember is that we need to factor the numerator and denominator before simplifying. So we need to factor the top and factor the bottom. And we also should state the non-permissible values. Now, just for time's sake, I might skip through that a little quickly, but I always wait, when I'm stating the non-permissible values, I always wait the factor first. So factor the bottom first, then state your non-permissible values. Alright, so if you look at this guy, excuse me, I can factor out a 4 out of this guy. So I'm going to factor a 4 outside, so I'm left with 4, and I'm converting back and forth between x's here, the style of x's, guys, so don't get confused, they're all x's. 4x minus 1, and And like I said to you guys in class many times, when you do this, just do a quick mental check to make sure if I multiplied back in through, I'm going to get what I started with. And the bottom here, again, this is a difference of squares. X squared minus 1, you got a perfect square, and you get a perfect square. So you end up with x minus 1, x plus 1. So if you look at the bottom here, my non-permissible values, x cannot equal 1, x cannot equal negative 1. So those are my non-permissible values. So now I got to look to cancel. So canceling, guys, is always, for some reason, people find it very difficult. But basically, you just got to look for things that are the same. And we're not dealing with extremely complicated expressions right now. But for the most part, if you have something the same in the numerator as it is in the denominator, then you can cancel. As we get into more complicated expressions, you got to sort of be a little bit more careful about that. So here we go. I got x minus 1 in the top, x minus 1 in the bottom, and then I have my final answer, 4 all over x plus 1. So that's my equivalent expression. This guy is equivalent to that guy. So that's a fair example of something that you might see on a test or in class. Not an overly hard example, but it is a good example. Let me throw something a little bit harder at you. Let's try this guy. Let me see if I can't make this a little bigger. Alright, so again, first idea is make sure you factor. So we got to factor this guy. So it adds to get us 3, multiplies to get us 2. Well, that's going to be x plus 2 on top, stays the same. So on the bottom, we're going to have adds to get us 3, multiplies to get us 2. That's going to be 1 and 3, so x plus 1. Sorry, 1 and 2, x plus 2. And there I go, changing between x's. So then, my non-permissible values, x cannot equal negative 1, and x cannot equal negative 2. Anytime if you have either one of those values on the bottom, it's going to give you a denominator of 0. So then I got to cancel, so I'm looking at, well, I can cancel this guy with this guy totally. And then I'm left with, so there's nothing left on the top except the 1 that was originally in front of this guy, all over x plus 1. So there's my simplified rational expression, which is equivalent to this guy. Let me try one more and call it a day. So this one's even more complicated still. So we have the top we need to factor. So again, that's AM method. But adds to get us negative 1, multiplies to get us 6. Well, that's going to be x minus 3, x plus 2. So adds to get us negative 1, multiplies to get us negative 6. And the bottom, we just have a common factor, so we can take it to 2x outside. 2x. And I'm glad we actually had this example. Take a 2x outside, so I'm left with here. I'm just left with x plus 2. And with these, again, really good idea to do just a quick check to make sure I get back. So I get 2x squared if I multiply these two, and then if I multiply these two, I get 4x. So it's good to go. My non-permissible values. This one always throws people for a loop. My non-permissible values here, I got to be careful of this 2x. If x is equal to 0 here, then that entire thing is going to be 0, so x can't be 0. So make sure if you got just an x or 2x or a 5x, whatever x outside, that's going to be a non-permissible value of 0. Anytime you don't have the c term of your quadratic on the bottom, the plus c or the plus a number, the constant, then you're going to have a non-permissible value of 0. And this guy itself is just going to be x cannot equal negative 2. And here we go. Let's see if we can't do some canceling. So I have an x plus 2 here and an x plus 2, just like this. So cancel out the entire thing. And then I'm left with x minus 3 all over 2x. And it's situations like these, guys, that people want to just, they try to look for something when nothing's there. I can't cancel out these x's. Because you got to remember that even though I'm dividing by a monomial here on the bottom 2x, that it's really just distribution property. I have to go to both. So if there's not something common in both of these because they're separated by a minus sign, then I can't cancel out. So I can't cancel out the x in this one if there's no x here. So there's nothing more I can do with that. I can just leave it. And I can, let me just bring up a blank page here. Perfect example of a situation like this will be something like this, where you have x plus 7 over x minus 7, or x plus anything over x or minus anything. People always have a tendency to want to cancel out the x's here. So they want to cross off the x's. But you got to remember that this thing, this entire denominator, has to be able to go to both things when they're separated by a plus or minus sign. So really, in other words, this thing is basically x minus 7 plus x over x minus 7 over x, 7 over x minus 7. So it has to go to both. It has to distribute to each thing inside the numerator. The reason why that's a little different, if you go back to this example, the reason why I can cancel out these two is because these are separated by a multiplication sign. So it's a situation similar if you had 3 times 2, over 5 times 3. So I can just cancel these guys just like that, because I'm just multiplying by 3 on the top and multiplying by 3. I'm multiplying by 1. I'm multiplying that by 3, multiplying that by 3. Well, it's the same situation here. I'm multiplying by x plus 2 over x plus 2, which does nothing. It just it changes a little bit, but it's still equivalent. That's why we can cancel. That's exactly why we can cancel. So my recommendation for you guys, of course, is finish up homework set 1.6, which you will have soon. Page 317, 4, 5, 6, 8, 15, 17. And there are lots of great questions in that chapter. Just because I assigned these guys doesn't mean that's the only ones. There are lots of great questions. And I have full work solution to all those questions. Hopefully, this gets the unit off to a great start. I'll make more videos if you guys watch the videos and they help. And I'll see you in class. Thanks.